A solubility product is the equilibrium constant describing a solution at the saturation point of a salt. So for salts with a given formula type, if they have the same formula type, such as the metal that I've represented here with capital M and its counter ion X, if they have the same one, then a larger KSP means greater solubility. But if they have different ones, it affects the form of the equilibrium constant, so you have to follow through a calculation of solubility in order to determine which salt is more soluble and to get the final solubility. So let's look at a couple of examples here. Starting with a simple one here that's just AgBr, silver 1 bromide, and we want to calculate the solubility in molarity if the KSP is the value given. So we start with a balanced equation, and it's an equilibrium constant here, so we have equilibrium arrows. Now this is the form mx 1 to 1 here, so just to take it back to what we had earlier. And that's a solid, breaks up into an ion that's aqueous and another anion that's also aqueous, 1 to 1 stoichiometry. And so if we're thinking about an ice table for any equilibrium condition, which is what we have here with KSP, we don't care about the solid because it doesn't go into the equilibrium constant expression, and we start with nothing in solution for our two ions. We don't have a common ion effect in play because we're just dissolving silver bromide. Now the change, we're going to add a stoichiometric equivalent of our silver, and we're going to add an equivalent of our bromide to solution for every one of our silver bromides that break up. Here, give me a little more space. There we go. And what happens here is we have to think about what our KSP expression looks like, and it's just like this, 1 to 1. And so we raise to the 1, no problem there for our expression. Now what do we get? We get x and x at equilibrium, so x squared is equal to our KSP. And so we can take the square root of our KSP, and we'll get 5.7 times 10 to the minus 7 molar for our solubility. So the x value that goes into our ice table is always our molar solubility for these KSP expression calculations. So 5.7 times 10 to the minus 7 molar is our solubility, moles per liter. And we get that same concentration of each of our ions in solution at the end. Now let's see how the form changes here. So our second value for solubility, calcium fluoride, but notice we've asked for grams per liter, so we're going to have a little bit of an additional step, but we're going to start the same way, balanced equation, calcium fluoride, it's a solid. It's going to partially dissolve into calcium ions, but 2 equivalents of fluoride ion per formula unit of our salt. So we have to put that 2 into the stoichiometry. Well, for our ice table, don't care about the solid, it doesn't go into our expression. We get 1 equivalent of calcium, but we get 2 for fluoride, and technically that should be what we add, our change in initial change then equilibrium for ice table, starting with nothing, and our equilibrium concentrations of our ions will be x and 2x. So now, with our equilibrium constant equal to 3.9 times 10 to the minus 11, we care about stoichiometry all of a sudden, because our mole ratio for fluoride is 2, we have to square the term for fluoride. And so we end up with x times 2x, but that 2x is squared. And at this point, we end up with x times 4x squared, which ends up being 4x cubed. So we have to divide by 4 and then take the cube root, and when we do, we get 2.1 times 10 to the minus 4. moles per liter, but we're not asked for moles per liter. That is our solubility. We are more soluble than our previous silver bromide example because we got a bigger number for solubility, but we were asked for grams per liter instead. So write out our units. Moles of what? Calcium fluoride per liter. Well, there are 78 from the periodic table. Molar mass, 78.07 grams of calcium fluoride per mole. Moles cancels. We're now in terms of grams per liter. That number comes out to be 0.017 grams per liter solubility of calcium fluoride. Or it's the amount of concentration in solution for calcium, but if you wanted the amount of concentration for fluoride, remember that's equal to 2x, so we'd have to multiply our solubility values here and here by 2 to get fluoride concentration.